Today we are really taking it to the extreme. From a DIY project to a spectacular setup. Despite their simplicity, they are pretty powerful. In earlier videos, we explained their working principle and affordable DIY suggestions. Today we are exploring how far spectacular designs can boost a VLF antenna's performance. Okay, but what potential is still there? In a nutshell, their small electrical size results in a low antenna gain, and their tiny radiation resistance is causing an extremely low efficiency. So far, we were using large loops and suitable impedance matching to achieve good reception. Now we are boosting their efficiency. Before we move on, I just wanted to say thank you for recent comments and emails. It's a fantastic community. I received great reports, tips and excellent questions, inspiring new ideas. From a given electromagnetic field strength, VLF loops are actually only converting a tiny fraction into a receiver signal. It's rather unusual to consider all these properties individually, but in order to understand the extreme properties of VLF loops, we need to break down factors such as directivity, theoretical gain in main beam direction, efficiency, and impedance matching. Directivity is varying between 0 and 1. It can maximize signals or null out interference. Proper impedance matching is achieved using such a network. You're more than welcome to watch the earlier videos about it. Now, let's explain two almost unbelievable facts. In general, gain in main beam direction equals an antenna's effective area divided by the effective area of an isotropic antenna. While the isotropic antennas is gigantic, at like 15 kilometers wavelength, the loops just equals its geometric area, resulting in very low gain. This diagram is showing signal levels at a certain electromagnetic field strength, giving you an estimate of larger or smaller design's performance. As you can see, size makes a huge difference, but of course there are limits. This equation is determining its efficiency. Unlike other antennas, it's tiny, even when losses are only milliohms, since its radiation resistance is extremely small. But that's exactly why there is great potential, as we will see in a minute. As you can imagine, I'm not suggesting a 2-kilometer vertical loop for 20 kHz. Instead, we are seeking a practical design. Let's assume this volume is available for the antenna. It's 1 meter in diameter and its cross-section is 20 times 20 millimeters equals 400 square millimeters. Conductor's cross-section totals in 250 square millimeters, the rest is for insulation. The effective serial resistance of a resonant capacitor is 10 milliohms. Considering the constraints, we are now seeking a winding design delivering the best efficiency and signal level, considering losses, number of turns, skin effect, etc. First, we are computing its properties when using 2.5 square millimeter copper wire for 1, 2, 3 turns and so on. 100 turns would fill the specified cross-section. While its absolute efficiency remains low, it is growing by 2 orders of magnitude with more turns. Interestingly, it would be much better at higher frequencies despite greater losses due to the skin effect. It's pushed up since radiation resistance is increasing to the 4th power as the wavelength decreases. As expected, the signal level is also increasing with the number of turns. To put the performance increase into perspective, I'm comparing a 5-turn resonant loop that we tested earlier. For example, if we built 20 turns instead of 5, it would produce about 8 dB more signal. Just as a side note, the signal of a non-resonant 1 meter loop would be below -97 dBm in this diagram. For the second simulation, we are utilizing the entire cross-section from the very first turn. With 2 turns, the conductor would be thinner, with 3 even thinner, and so on. Compared to the previous results, its efficiency is increased at few turns. However, the skin effect is still causing a drop as long as the conductor width is greater than penetration depth. There's a similar behavior on the signal level, which is hardly increasing for more than 40 turns. The next strategy applies conductors thinner than twice the skin depth in order to avoid the skin effect. A conductor's bundle, connected at its end, is effectively creating a lids for VLF. Greetings to the viewer who suggested we try RF lids. Its schematic is looking like this for 1 turn, 2 turns, 4 turns, etc. Flat conductors would be an alternative. Interestingly, efficiency is now independent from the number of turns. The signal level is almost reaching its maximum at 10 turns and is hardly increasing further. So far, suggestions are not really spectacular. My favorites would be flat or bundled conductors. 14.6 dB better signal would justify the effort. Next, let's investigate really wide cross-sections. The loop's diameter remains 1 meter. Knowing its actual performance, our 5-core cable loop is the reference, delivering -82 dBm signal at a specific field strength. In the second line is the 20 by 20 mm cross-section loop we just optimized for 14.6 dB more signal. Now we are computing the potential of truly elaborate designs by doubling its width, respectively quadrupling its cross-section step by step. Look at the weight. 30 kilograms might be manageable for hobbyists, but beyond that, the antennas are becoming incredibly heavy. But boosting its efficiency by a lot of conducting material, you can theoretically grow the signal 35 dBs compared to the reference. This would be certainly more than 50 dB compared to a non-resonant loop of the same diameter. I must admit that's only for extremely ambitious hobbyists. But perhaps you have seen some in professional installations on ships, for example. Let us know in the comments. And in case your energy provider accidentally left a large cable drum in your backyard, you can still make a cool VLF antenna out of it. There's great potential, however it only works with resonant loops. I think I will build a low-weight version that I can use indoors. Efficiencies of resonant shortwave loops can reach double-digit percentage. You cannot achieve that in the VLF range unless you could use superconductors. Hoping you got some takeaways for your own projects. In an upcoming video, we will cover an interesting DIY suggestion for frequency tuning. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.